to this video of backpropagation. In this video, we'll not only be covering basic concepts of a feed-forward network and backpropagation, but we'll also go slightly deeper into the mathematical and conceptual understanding of this topic. This is very necessary because backpropagation is not very simple and the mathematics is not as simple as what we did in the case of linear regression or even linear classification models. We will be using those links in the description, so if you have not seen those videos, please have a look. So let's deep dive into our discussion. So let's start with the discussion on neural networks. What is a neural network? Let's do a very basic recap. So what you see over here is a very simple network. I have got one input layer consisting of features x1 and x2, and since you're numbering these layers, I'm assuming this as layer number 1, and then we have layer number 2, and this is layer number 3. There are two nomenclatures of representing such a network. Either we call it 3-layer network including the input and the output layer, or we can call it just one hidden layer network. Okay, so it is either one hidden layer network or it's a 3-layer normal network. Until this stage, this is a artificial neural network or an ANN, and if we have more than one hidden layers, that becomes a DNN. But we would be representing it in a general concept of only neural networks. For the purpose of backpropagation, that remains same all across. Now, why finding or optimizing error in the case of backpropagation is slightly different and also slightly difficult in terms of linear regression? Let's understand that, and that intuition should guide us to the mathematics of the backpropagation. So let's do a recap on our linear models. Okay, let's assume we are talking about linear regression first in its basic form, and then we may also consider a basis function linear regression. We have also done a detailed video on basis function regression, so if you have not seen that, I'll link the video in the descriptions below. Please have a look at it. So in this particular case, we had just one you can say a function, and the input was coming to this function, and there was some weights that we attached to it, and we had the output. This was very simple in this particular case, and we said that our loss term is nothing but our error plus our regularization. We also have a detailed video on regularization, so if you have not seen that, please see the links in the description below. And in the case of neural networks, since we will not use regularization in this particular form, we'll use some other form of regularization, so we are assuming loss is equals to error in this particular case. And assuming we are going for an L2 error or square error, we could have simply said that loss is equals to our target minus output whole square, and we'll take a summation of that over the complete data set, which is n is equals to, say, d to d representing the entire data set, and since it's a mean, so we'll do a 1 by n. Okay, and the differentiation of this was very simple in the terms of weights. Now let's try to use the same analogy in the case of neural networks. Now we also have an output in this particular case and a target in this particular case. So we have the target, which is the actual given over here, and suppose this last unit gives us an output, okay, which is given by O. So we can use a similar notation for the error function over here, and we can use similar square error, so we can say sigma of t minus O whole square, and if we have a number of data sets, then we can have n is equals to 1, sorry, this is not d but this is 1, or rather d is equals to 1 to capital D, which is the total number of records in the data set. And to make things simpler for us later, we'll just add a constant outside that will not make any difference in the gradients, but it will simplify our mathematics and we'll explain that. Okay, but now the problem is this will help us only optimize weight for the last layer. But the error that we are getting, or the output that we are getting, is not just a function of a last node, which is this one. It is actually a function of all these nodes. So in essence, what we are trying to say over here is that this network is not one linear regression, even if it is a linear regression, but 5 linear regressions going on. And we have one error or one output which represents all these nodes in the network. So if we have 5 nodes, so, or say a number of nodes, this output is a representation of all these 5 nodes. Or if you're talking in terms of weights, that is what is our objective, because even in this particular case our output was simply omega transpose x. Okay, and here x is, we have added an x naught for the bias, so this term is in matrix notation. In simpler arithmetic notation, it would come to w naught x naught plus w1 x1. Suppose if there are two features x1 and x2, then it will be w2 x2, in which case x naught we have assumed is equals to 1, which is a bias. So this w naught is the bias for us. Okay, and we were just differentiating that with respect to our weights, weight vector. Okay, so we were just doing a delta E divided by delta W, where E is equals to this much, and it was very simple for us. But now if we want to do a delta E by delta W, we do not have one weight. How many weights we have? If we have 5 neurons, we do not have 5 weights. Let's see. So this is one weight which we'll call like 1 1 to say 2 1. Okay, so W, so this is layer 1 cell 1 to layer 2 cell 1 to 1. This is W11 to W22. Okay, and now you can understand 1 2 3 4 5 6. Okay, so just in this small network we have 6 weights. Okay, and your weights will increase at the order of omega n square, because one each will actually feed into all of those layers. Okay, and assuming you have only one layer. If you have multiple layers, then also in a feed forward network it will be going only to those layers. So again it will be uh, in terms of inter layer weights, it will be n square or n into m, depending if they are different number of neurons. Okay, so we are talking about, in this particular case, 6 weights to be optimized. This is the challenge in the case of neural networks as compared to linear regression, despite the facts that most of the things remains the same. Okay, so now let's try to, once we have understood the problem, we'll solve it mathematically and see what is there. Again, coming back to our basic network, so this was our input layer, this is our hidden layer. I'm putting the hidden layer in white. Okay, and suppose this is my output layer. Okay, and let's toggle the connections. So we are assuming each node is connected to every other neuron or node. This is called a dense network. Okay, so we covered one more terminology, dense network or a dense layer. In which every neuron is connected to every neuron. So to make things simple, we'll assume that this is a linear or an identity activation. Identity activation is a special case of linear, where your multiplier may become 1. Okay, and this is our first assumption to make things simpler, and then we will cover everything. Okay, and what is activation in this particular case? Let's spend a moment to understand that. So let's assume one particular neuron, say this particular neuron that we are talking about, and assume case of linear or logistic regression, we said that the output of this particular neuron, okay, or let's call it Z, was sigma of omega I xi, okay, where I is equals to 0 to a number of input layers in this particular case. So these two are the input to this. So the weights of this is W1, W2 in this notation, but otherwise we'll have to add the layer number also. But to make simple, we are just assuming this over W1 and W2. Okay, and the X is what is the signal coming from this and this. So for the purpose of this neuron, this becomes X1 and this becomes X2. Okay, and as in the case of linear regression, we'll add bias, and we'll add a bias in similar way. So we'll call this as omega naught, the weight of it, and this is X naught, which is the bias term for this particular hidden layer. Okay, and that is why I here stands from 0, not 1, and it goes from 0 to 2 in this particular case, or the number of neurons, say n. Okay, this was Z. But neural networks, as compared to the simple linear regression, are more sophisticated because they can add nonlinearities, and they add nonlinearities in the form of activation functions. If you have seen our video on basis function, this is very similar to the basis function. So you can assume this to be 5 basis functions going on into one neural networks. But here the difference is that all the 5 basis functions could be different, and here we attach basis function not to individual weights but to overall output from the weights. So these are the difference between the basis function and the neural networks. Okay, so in case if we add activation, then our Z, which is the final output, which is this one that is going now. Now this is Z, not X. So this becomes our Z, the output of this particular gauge, which becomes X for the next neuron. So Z of I is equals to your activation function of, sorry, this is A of I. So A of I, which is the activation function or the final output, so this is your A of I, okay, which becomes your Xi for this particular neuron, the output from this hidden layer node, is equals to your activation function into Z of I. Let's call it I. Let's assume this is a small notation so that we have a consistency between capital and small. So this activation function could be of different types. The most simplest for the inner layers is sigmoid, which is very similar to what we did in logistic regression. Okay. For the output layer, depending upon what type of output layer it is, whether if it is like a binary classification, it can be sigmoid. If it is a regression sort of a problem, as the example that we are doing over here, this could be linear or identity. Okay, and sigmoid has its weaknesses, so you could have used tanh over here, that could have given a similar treatment, but because of the weaknesses in sigmoid and tanh that we'll discuss later in some of the other videos, there could be anything. It could be a ReLU, and there are multiple variants of ReLU, p-ReLU, or advanced form. It can be considered as a different variant in itself, eLU, and there are other leaky ReLU and so on and so forth. There are multiple variants, but we'll call them as activation function. Then there is a terminology called link function, which is nothing but the inverse of activation function. Okay, but now we will restrict our example to linear and sigmoid. So we'll assume linear outside and sigmoid inside, and then we will convert the outside also to sigmoid. Okay, so in case of identity function, this will be a will be equal to same as your z. Okay, and this is your identity, or maybe some multiplier of it. And in the case of sigmoid, it will be becoming a sigmoid function of zi. Okay, and what is sigmoid function of x? This is given by 1 upon 1 plus e to the power minus x. Okay, so this is sigmoid. Okay, now coming back to our discussion on how do we solve that particular problem. So now let's draw that network again. We have two inputs, two hiddens, and one output node, and we are constructing everything. We are assuming a dense network. Okay, but for there'll be different cases for the output layer and the inner layer. The mathematics will be slightly different, but at the end it will actually converge. So to make things simpler for us, we will just assume for the output layer and then we'll move to the inner layer. So for the output layer, again the error could be termed as sigma of your target minus the output from the last layer whole square, where n is equals to, or d is equals to 1 to d, and we said we'll add half over here. Okay, now let's try to break this up. And we already discussed that this is an identity function. So in the case of identity function, our aj is equals to our zj, assume this is the jth layer that we are talking about, is equals to, and let's add bias if we want to, omega naught x naught plus omega 1 x1 plus omega 2 x2. Okay, or for the moment, to make things simpler, just forget the bias, but it will be the same mathematics with or without it, because this will be constant. And in matrix notation, we can call it omega transpose x. Both will be the same thing, we'll use them interchangeably. So if we expand this notation, and I'm not adding d is equals to, but you can understand it. In fact, this should have also been d and d. So now I'll skip all the d's. T minus omega 1 x1 plus omega 2 x2. Okay, and this whole square 1 by 2. Now this is interesting, because here omega 1 is coming from some other neuron and omega 2 is coming from some other neuron. Okay, and we are talking about this. So omega 1 and omega 2 is the input to this, and this is the x1 and this is your x2. So this is your x2. So omega is of the linkage and x is what is coming from here. So when you're talking about this, the aj that is coming from this will become the x for this particular neuron. Okay, so how do we actually differentiate this e? If you want to minimize it, we have to differentiate it. So we would have to find it dE by d omega vector. Okay, which is equals to delta E over your omega vector, which is omega 1 and omega 2. Now let's try to understand this concept. Just pay attention over here. So suppose if I have a two-dimensional vector, okay, W1 and W2. I draw this as W, or this is actually not W1 and W2 but delta W1 and delta W2, and this is my delta W. So this is my complete differential, and since the components of W are W1 and W2, these are my partial differential. Okay, so in calculus, if we have not gone through, partial differential is a differential only with respect to one of the components of the constituent. Okay, but if this is vector, and that is what we are assuming, so all these are multi-dimensional vector, and each dimension correspond to one of these W's where that neuron is coming from. This could be represented in vector notation as a sum of this. This is a projection of this final vector W on the first vector, first dimension of the vector, and this is the projection on the second vector. Okay, so this is your delta dw1, or dw1, delta is already there, and this one is the projection on dw2. Okay, and if we just do a vector addition of that, this will give us this final vector. So in a sense, what we are calling is that delta E and by delta W, okay, which is equal to what we have written over here, delta E of vector of W is nothing but a constituent of our delta E partial differentiation with the first vector, first omega, delta E, these are its constituents. Okay, so for a multi-dimensional differentiation, we discussed contours in some of the videos earlier. I'll put a link over there. This was a similar concept. Now instead of this 2, 3, this can be like multi-dimensional, and each of that will be a constituent of this. Okay, so now instead of computing delta E by delta W, we can actually compute two different things, delta E by delta W1. What will this give us? This will give us a partial differentiation of the error with respect to this linkage. Okay, which means now we can optimize the weight W1 separately by just doing a partial differentiation of error with respect to W1, and we'll repeat that same process for W2. Thereby we can optimize the differential with respect to W2, and we can get the optimal value of W2. Okay, if you don't understand this concept, please pause, rewind, and just see this last 4-5 minutes. It will be helpful. Okay, so now instead of finding it with respect to complete W, and because our objective was to just optimize the weight for these two branches, we could actually do it separately by doing a partial differentiation with respect to each of these W1 and W2, and that is what we'll be going. We'll be computing delta E by delta W1 and then delta E by delta W2 separately, and we'll put that as 0, and then we can compute our final W. Okay, so how will computing a final W? So suppose we have to compute delta W, and we are calling that this is equals to delta W plus the learning rate. Okay, neta. So now neta is equals to learning rate into your delta E by delta W. And this is actually not plus, but this is minus y because we go in the opposite direction of the gradient to minimize it. And the same concept arises for the partial differential, and we can actually visualize the partial differential also. So on a 2-dimension map, if you were seeing the contours, it would have looked something like this. We explained this explanation in the bias variance chapter and also the Bayesian video. Please have a look. But now since we have disintegrated that into W1 and separately and W2 separately, now you have two different maps. You can assume it this way, W1 and W2, and you may actually find some different shapes in this. Okay, and what we are doing is we are finding this particular gradient, which is our delta W1, and we are finding delta W2 separately. This is equal to delta E by delta W1. Sorry. Okay, similarly this. And once we find this, we just reduce our previous delta W1 by this learning rate. Okay, this is what we're doing. So this component gradient, the direction of the gradient is this. Okay, we multiply it by the learning rate, and if this is our initial position, this our initial position is this, then if we go down, which is a minus sign, then we reach over here. This is suppose neta learning rate, so this final position is nothing but this. Okay, and we do a similar thing for this. Okay, so this is the brief conceptual understanding of the partial differential part. Again, if you do not understand any part of it, please go back, because we'll be building on this concept more and more. Okay, so we'll solve for W1, and for W2 it will be similar. So now if we have to do a delta E by delta W1, okay, and our E, as we discovered earlier, was sigma of your target minus your output whole square, which we expanded to target minus, and we were assuming identity activation in this particular case, so it became for us W1 x1 plus W2 x2. Okay, this is whole square. Just a recap for the people who needs a recap on the basic concepts of calculus. So there is something called a chain rule in derivatives. We'll be talking about chain rule in backpropagation also, but this is actually coming from derivative itself, but this what we're talking about is the chain rule for derivative. Okay, so if I want to differentiate a function with respect to something that is not in that function, so suppose my function is a function of x, okay, we can still differentiate it, but we have to do it in two steps, and both the two steps would be chained as a multiply. So we can do it as df. Now f could be differentiated only on the basis of x because it depends upon x. We can do a df of our dx, and then we can chain our differential of x on y. Okay, now assume this as a whole function with its square. Okay, so first we will differentiate this, assuming this is a whole function, and then this we will differentiate the inner part. Okay, so coming back to, if we want to differentiate it with respect to W1, so now this is our error, and we are differentiating error with respect to W1. Okay, this would be, now 2 would come out. Now you can understand why we have kept half outside, because we can actually cancel it and make it simpler. Summation will remain. Okay, now it will become t minus, and to make it short I'll call it O again. So this was the expansion of my output, so I'll call it O to be concise. So this is my first differential. Now I'll take the inner part, okay, and now I'll try to differentiate that with respect to W1 multiplied by, if you see this is constant with respect to W1, so this is 0. Okay, this one has W1 and this is linear on W1 with x1, so minus x1. Okay, again this part is constant with respect to W1. Okay, so this is not dependent upon W1, so this would be again 0. Okay, so our delta E by delta W1 and this cancels out, is equals to t minus o of minus x1. Okay, now suppose we are going for a single instance. Okay, so this was over the complete data, n is equals to, or d is equals to 1 to d, capital D. This is your batch gradient descent. In case if you are going for a stochastic gradient descent or an element-wise gradient descent, also called an online gradient descent or stochastic gradient descent, we will not require this summation, because then for each movement we would actually move by your neta, and in that particular case your neta batch will be different and your neta online will be different, and neta online will be quite smaller. We'll discuss why. In fact, we can discuss it here itself. So suppose, let's use some other color. I am going down in this particular direction of my delta E by delta W1, okay, by neta. If my neta is large, what will happen? I will go down over here. Next time I would go down, suppose somewhere over here, and suppose this is my minima. Next neta, what will happen? Next neta, if you see, we'll actually cross this minima and then we'll go back to this side. Okay, and then if you have to come back in the next iteration, now the direction of your delta E by delta W will change, and if you want to work again, you will come over here, and then with next iteration you can go back over here. So you'll keep hunting around the minimum, but will not touch the minimum if the neta is very high. Okay, and since now this neta is computed on an online manner in the case of online gradient descent, so it needs to be slightly smaller or much smaller for your online gradient descent. Okay, I'm not using different notation for neta batch or neta online, but you can get the idea. Okay, so essentially what we have discovered up till here is that my delta E delta W, and I'm assuming for one particular instance, so I'm not putting a summation, is equals to, let's call this part as the error, okay, which is t minus o, okay, error of ith node, okay, is equals to delta I xi with a minus. Okay, this is minus. Okay, so this is our important takeaway from this slide, and then we will go back next. Okay, copying back again, delta E by delta W1 is equals to minus time the error, which was the output, target minus output, and my xi, which is nothing but the input signal coming on that particular weight, this particular weight. This was the input signal that was coming. So now if I am computing my final delta wi with each instance, okay, this would be equal to my initial wi, okay, minus times it was neta delta E by delta W1, and now we will replace this value over here, so it becomes initial delta W1 plus times eta delta I xi. Okay, and we will remember this because this will be helpful for us in building more complex use cases that we are going to do next. And similarly, you can copy this for whatever number of weights are there for the final layer. Mostly this neta is taken same for all the weights, but there are different ways you can actually add momentum and other things. We'll not go into that depth. In this particular case, this will become x delta 2 x2. Okay. Now up till here it was simple. Okay, and up till here we were only dealing with the output layer with an identity function. So this was our network, one input layer, one hidden layer, again 2 nodes, and one output layer. Okay, and to make things simpler for us, we assume that this has an identity activation, in which case this was mostly a regression problem. Okay. Now we'll make it slightly more generic. We'll call it say binomial classification problem, and in which particular case we will use this as a sigmoid function. Okay, and it will not remain identity. Now let's try to derive it for sigmoid function. What will be this particular equation? Okay, again coming back to our error, this remains the same, and we'll start from here again. This was t minus o, if you remember, and then whole square. And now in this particular case, this o is actually a function of your x, not exactly omega 1 x1. So half of is equals to sigma. Okay, and sigma is equals to sigmoid, which is equals to 1 upon 1 plus e to the power minus 1. Okay, sigma of what was the input coming, which is w1 x1 plus w2 x2. Again, you can add the bias. I'm just skipping the bias for simplicity. In that case, it will be w0 x0 plus. Okay, so this in that case becomes t minus sigma of omega 1 x1 plus omega 2 x2 whole square. So if we are doing a partial differentiation of this with respect to w1, again 2 comes out, and this becomes t minus sigma, let's call it z. This part is z for me, so this is output is equals to sigma z. Okay, and we can expand it, but for the conciseness I have just put it as z. Okay, multiplied by, again remember the chain rule of derivative that we talked about. Now this is a function of x. Okay, so first we will differentiate this, and then when we come back over here we will have to differentiate it by x again. So what we are trying to do here is, so delta f of g of x, if I have to differentiate that with y, okay, I have to actually do a 3-level chaining. So okay, I can do a delta f by say delta g, and then I can do a delta g by delta x, and then I can do a delta x by delta y. So this is exactly what we are trying to do, and so we'll have to differentiate our activation function by x. Okay, and now let's compute the activation function's derivative. So we are calling sigma x this is a sigmoid function, 1 upon 1 plus e to the power minus x. Okay, and we are trying to differentiate our sigma x with respect to x. Okay, so what will this be? So this could be written as 1 plus e to the power minus x whole raised to power minus 1, because this is in denominator. Differentiate this with respect to x, so this minus 1 comes out. Okay, and then we again get 1 plus e to the power minus x, but since now we are treating that as a function and there was minus 1, so we reduce one power and call it minus 2. Then we go inside, so one differentiation of 1 is 0, that's a constant, and e to the power minus x is minus 1 for this particular x into e to the power minus x again. Okay, so this minus minus gets cancelled, so what we are left with is e to the power minus x, and we will take that minus 2 down, so it will become 1 plus e to the power minus x whole square. Okay, so now let's try to bring it back in the form of sigma. We can write this as say 1 upon 1 plus e to the power minus x. Okay, and then another this now e to the power x upon the left of 1, because we have already taken 1 power outside, so what is left is another e to the power minus x. Okay, now for the second term, this first term, if you recognize, we started from here, so this is actually sigma itself. Okay, into second term, if you see, just try to add 1 and subtract 1, this could be written as 1 plus e to the power minus x, and since we have added 1, we can do a subtracted 1. Okay, upon 1 plus e to the power minus x. Okay, and if we are trying to expand this again, this could be written as this sigma outside, and this whole factor could be written as 1 plus e to the power minus x upon 1 plus e to the power minus x minus 1 time 1 plus e to the power minus x. So this minus 1 and this separate. Now if you recognize this, this is 1, same thing, this is again sigma. Okay, so sigma minus 1 minus sigma is the differential. So d sigma upon dx is nothing but sigma x into 1 minus sigma x. Okay, so just remember this, we'll be using this and completing what we left. Okay, so coming back to this slide and following the chain rule, what we discovered over here, we can write differential of e to the power w1 is, okay, we left over something. So now let's go back to the initial color. Okay, into differential of sigma x, so we can write sigma 1 minus sigma, we discovered that. Okay, and then it will be the same thing that we did earlier, which is minus times into minus 1 of x, and in this particular case again this is x1. Okay, so this was the third part that we did. This whole internal whole differentiated by w1, and this again became 0 and this came out. Okay, so from the earlier discussion, again this gets cancelled out, and this is our delta, because this in this case this is the output, t minus output is what we are calling as delta. Minus gets cancelled out, sorry, minus comes outside, so minus times this is delta 1 x1 into our differential of the activation function. Okay, so in the case of sigmoid, the differential is 1 minus sigma into 1 minus sigma, but in general if you want to write, it will be the same thing that we discovered earlier multiplied by the differential of, or let's make it simple, activation prime, let's call it this way. Okay, this is a differential of your activation function with respect to x. So this is a general notation. Okay, and since we are assuming all the internal nodes also to be sigmoid activation, so we'll use this particular notation. So now let's see if we can actually solve an example out of it. So again, these are our input nodes, this is our two hidden units, and this is our output. In this particular case, we are assuming that our output is a sigmoid activation. Okay, so suppose and my final target variable is a binary classification, so it will be either 1 or 0. Okay, so suppose my inputs are, say, x1 is equals to 0.5, x2 is equals to, say, 0.3. Initially, when you start a network or initiate a network, we have to assign random weights, and these random weights are kept very small, so maybe in the range of 0.05 to plus 0.05, because if you keep a very large weight, it becomes difficult to actually optimize them if they are not correct. Okay, so suppose our initial value here is 0.02, 0.03, okay, 0.04, and say minus 0.05, and okay, we'll have to give this also. So I'll assume some numbers over here. So what is a feed forward mechanism in this particular case? So in the feed forward, we'll compute the values of the output for this. So suppose we are computing for the first hidden layer. So in this particular case, input is 0.02, weights is, and we'll assume a bias also in this particular case. So let me do a dotted bias. Again, a dotted bias for hidden layer to make it more realistic. And let's assume some weight for the dotted bias also. Okay, these are random, so I'm just putting any values, but you can actually generate a random number between these range and get something. Okay, and bias will initiate as 0, initialize as 0. Okay, so 0.02 into 0.5. Okay, so this is coming to here, and then 0.02 into 0.03. Here the bias is 0, so plus 0 into whatever is the weight for this, into 0.011. Okay, so this was your, suppose Z11, or this hidden layer, first hidden layer, or let's call it 1 only because there's only one hidden layer. And then we compute the output of first hidden layer, h1. Let's not call it output, that will confuse us, so let's call it a of 1 is equals to sigma of z1 is equals to 1 upon 1 plus e to the power minus z1. Okay, similarly we'll calculate for this at this. Okay, then suppose there is some output of from this particular class. So suppose the output or a out, this is what I'm calling a out, the output of this is 0.85. Okay, and if this class is 1, or then the actual output, which is t, is equals to 1.0. Okay, and our output in this particular case, this the probability is 0.85. Okay, so what is the delta in this particular case? Delta of output is equals to t minus o, which is equals to 1 minus 0.85 is equals to 0.15. Okay, and multiplied by the x1, this will give us 0.1. Okay, so after computing this, suppose my a1 is let's give it a new number, we can compute it, but let's say this is 0.22. okay, and my initial w1, I'm calling this as w, let's not call it w1 but call it like w1 to output. Okay, was say 0.04, we have marked over here. Okay, so now this becomes 0.04, assume any learning rate. So learning rate can vary from, say, very small number, say 0.001 will not go this small, because then it will do a lot of time to go down. But suppose we are using something like 0.101, you can take it to 0.1 but avoid going above 0.1, because otherwise it will start hunting the phenomena that we explained. So plus learning rate time, so this is the learning rate that we are using, into x1, and x1 here we have assumed as 0.22. And you remember this is plus, minus minus get cancelled out and becomes plus, so this becomes 0.04 plus 0.0022, okay, which becomes 0.0422. So this becomes a new value of W1, 0.0422. Okay, and so on and so forth. And similarly you will do for W2 out also. So this W1 out, and then you will compute W2 out. Okay, but now what happens next? So what happens next is now you have to optimize these weights also, which is coming from your input layer to this hidden layer. Okay, and without optimizing this, you cannot actually go back and optimize this, because the final output was dependent not only upon these two weights but all these weights. Okay, so till you do not optimize all these, you cannot go for the next iteration of optimizing these two. Correct? But there is a problem over here. So first we will discuss that problem, and then we will solve it mathematically to see what is the solution of it, or simpler solution to it. So let's first identify the problem. So this is our input layer, this is our hidden layer, and this is our output layer. So for the first step, what we did currently is we computed these two, W10 or one output and W2 output. Okay, but now we are left with 1, 2, 3, 4 more weights. Okay, and the easiest part that we discovered to optimize these weights is that delta E by any delta W is by doing this. Okay, but in our case delta E had one component of delta W, so delta E was T minus output, which was again suppose in the case of sigmoid of delta 1 x1 plus delta 2 x2 whole square, and whatever you want to add subtract. Okay, so this one had W1 over here, so we could differentiate it with respect to W1. But if we are talking about or say W10 to be more precise in our notation, so now we want to do W input 1, or I want to say W1 or hidden 1, H1. Okay, and this, and we'll also have to optimize this. So suppose we are only dealing with this for simplicity, so this is W input 2 to hidden 1. Okay, now in this entire equation these terms doesn't comes. Okay, so I'm in short calling this as W, say let's call it 3 and 4, W3, and this is say W4. Okay, so this W3 and W4 doesn't comes into my error. So if I want to do a delta E by delta W3, I cannot do it over here till I go into chaining. So again we'll have to get into the chain rule. So what we'll do is we'll differentiate this with respect to the output of this, and then we'll differentiate the output of this with respect to this. So basically it will be the same thing that we did. We'll differentiate delta E with respect to the output of this particular node, say whatever was coming over here, let's call this as output as A J. Okay, so in this particular case we can call it as, okay, and then we can do delta AJ of, now delta AJ is again dependent upon these two components, then we can call it like delta 3 and 3 as W3. We have already done this earlier or similar like this earlier, and we can break this again further down into the components, and we will come to the same notation, which is the delta of this error. Now this delta corresponds to this output minus this input, so the output of this and the input of these, okay, into our final xj. Okay, and this component is nothing but our, okay, sorry, this component is nothing but our W's, these two W's that is forming our network, and the weights of these two. Okay, this is again by the chain rule. And now what is our delta? Now this delta is the initial delta. So earlier the delta that was transient over here, so suppose this delta 3, suppose or hidden 1 was equals to our output of hidden 1, sorry, target of hidden 1 minus output of hidden 1. This could have taken it straight, but the problem was that we could compute the output of hidden 1, but we didn't have a target of hidden 1. Okay, and since we couldn't compute this directly, we had to do a chain rule to compute it with respect to the final deltas error. Okay, which in turn gave us that for any of these previous layer, we can just have the delta of the node which we computed earlier, and then we can multiply it with the weights that is coming to it to get the deltas of the nodes previous to it. Okay, so if I have the delta for this node to start with, so this we computed t minus o, delta output is equals to t minus o, and this, in this case, t was given to us from the data. We could compute the delta of this, say delta hidden 1 is equals to delta of output multiplied by the weight that is being incident of it. Okay, so this is exactly what it is coming over there. And if you add of both these weighted things, this will give you this delta. So this is what is being added over here. Okay, so now it becomes very simple. So from our earlier example, now we take that delta and then we multiply it by the weight, and we get the delta for this. Okay, and then we keep adding the x part, which is, and x with respect to this is these x's that is coming over here, and then we can compute for these 4 layers, and then we can start the next iteration. So we'll do a feed forward. After that, we'll get the next output, we'll compare that next output with the next instance target, then we'll compute the weights or the delta of the weights, optimize this, then we'll compute the delta of the weights, optimize this, then do another layer of feed forward. So this will keep going till all of these weights do not attain their minima, individual minimas. So with this, we conclude our session on backpropagation, mathematical understanding and conceptual understanding. If you have any questions, please put it in the comment section below. Please do subscribe to our channel and like the video, and I'll be putting all the links of the different videos that we talked about as some references into the description size below. Thank you. Have a great day.